Good day, students. Well, welcome to our online physics class, and today we'll be treating the topic friction. Friction is an example of a force, and there are so many examples of forces. Your weight is a force, your upthrust is a force, tension, that's a force that acts along a rope, pull, push are all examples of forces. But friction is a very special force in the regards that it is the only type of force that tends to do the opposite of what every other forces do. Now, what is friction? What is friction? We are going to be looking at its definition, we are going to be looking at its types, we are going to be looking at its properties, and we are going to be going through some very serious calculation under friction. Friction is a force that acts between two surfaces in contact, and it prevents the relative motion of one surface over another. I'll go over that again. Friction is a force that acts between two surfaces in contact, and it prevents the relative motion, or it tends to prevent the relative motion of one surface over another. If I place an object on a surface, there is a frictional force that acts between the two. It is that frictional force that will not allow these objects, that will try not to allow, that will tend not to allow this object to move over the surface on which I have placed it. So friction generally is a type of force that tends to prevent motion from happening. It is also a type of force that tends to stop an already occurring motion. So friction is the only type of force that does not create motion. Instead, it does the opposite. It prevents motion, or it tends to destroy motion. So friction is a force. It acts between two surfaces in contact, and it prevents the relative motion of one surface over another. Please get that one. If this is a surface, therefore, and this is another surface, the friction acts between the two surfaces. So anytime you have any given surface, you already know the direction in which the friction is going to be. And there are three of such surfaces that we can have. A surface can either be horizontal, as shown here, it can either be vertical, or it can be inclined. So when you place an object on a vertical surface, you are sure that the friction is acting along that surface. When you place an object on an inclined surface, you are so sure that friction is acting along the surface. So the direction of friction, or the friction, the nature of action of friction is that it acts along the surface that you have placed an object on, because it wants to prevent the motion of that object on the surface. And if the object is going to move on the surface, it will move along it. So anything that is going to prevent it from moving along it must also be along the surface. So friction acts between two surfaces in contact. It prevents the relative motion of one surface over another. That is all about the definition of friction. There are two types of friction. Friction can be classified as either static friction. Static friction can also be known as limiting friction. Friction can also be sliding friction. Sliding friction can be taken to be kinetic friction. So friction can either be static, limiting, or sliding and kinetic. Now, what do we understand by static friction, and what do we understand by sliding friction? Remember that I said that friction prevents the relative motion of one surface over another. That means if an object is ever going to move on a surface, then there must be a force that must overcome that friction before the object can be allowed to move over that surface. There must be a force that must overcome the frictional force before that object can begin to move over the surface. The force that must be overcome before an object can move over another, is what is called the static or the limiting friction. So before an object can even begin to move over another, then you must overcome the static friction. You must overcome the static friction. The moment an object now starts to move, you have overcome the static friction. If the object is going to continue to move over that surface, then you must continuously overcome another type of friction, and that is what is called sliding. Because when you overcome static to make an object start to move, as the object begins to move also, as the object continues to move, there's a friction that is still set between it and the surface on which it is moving. And that friction must also be overcome before that object can continue to move over that surface. So the friction that you must overcome before an object can begin to move at all is what is called static or limiting friction. The friction that must be overcome before an object can continue to move over a surface is what is called sliding and kinetic friction. If I am going to push any object, if I'm going to have to push an object such that it at least leave that particular position that it is, then I must be ready to overcome the static friction that is acting between it and the surface on which I want to move it. Now, the moment it starts to move, if I need it to continue to move, I must continuously also now overcome kinetic friction. That is the friction that is set between it, preventing it to continue to move over another. So static is the friction that you must overcome for it to begin to move, and sliding or kinetic friction is the friction that you must continuously overcome before an object can continue to move over a surface. Generally, static friction have a much higher value than sliding friction, meaning that it is more difficult to make an object move than to make it continue to move. It is difficult for an object to start to move. It is more difficult for an object to start to move than for it to continue to move. It is a little bit easier for it to continue to move. You need to overcome a greater friction to make it move, and you need to overcome a less friction for it to continue to move. That is why generally it is easier for us to continue to move, for us to continue to do things, than it is for us to even start it at all. The tendency for us to continue to do something once we have started is higher. That is why they always tell you that it is more difficult to start, because it takes a greater force. It takes a greater movement before you can start to move at all. So frictional force is the static friction is a frictional force that must be overcome before an object can begin to move, while sliding friction is a friction that must be overcome before an object can continue to move over the surface. And there are so many characteristics that we can, or properties of friction that we can talk about. Properties of friction. Number one is what is part of the definition already. Friction always opposes motion. Friction prevents motion. Friction tends to prevent motion. Friction acts in the opposite direction of motion. For you to know the direction in which friction establishes itself, you need to consider only two things. Number one, you need to know the surface on which the object is trying to move. Friction is along that surface. If it is an horizontal surface, friction is horizontal. If it is a vertical surface, friction is vertical. If it is an inclined surface, friction is along the slope of the inclination. Now, if let us assume it is an horizontal surface, being an horizontal surface, the frictional force can either now be to the left or to the right. How are we going to know which direction to take? Once you can establish a direction for your motion, or the direction in which you want to create motion, friction ultimately establishes itself in the opposite direction, because friction will not want that motion to take place. So if you are trying to push an object to the left, you can be so sure that friction will establish itself to the right. If you are trying to push an object up on a vertical surface, then friction establishes itself downward. If you are trying to move an object up an inclined plane, friction establishes itself downward. If you are trying to move an object downward on an inclined plane, friction establishes itself along the plane upward. So number one property of friction is that it opposes motion. It is always in the direction that is against the direction of motion. Please always take that. Number two is that friction depends on the nature of surfaces in contact. We have already said that friction acts along the point of separation of two surfaces in contact. Now, the nature of the surfaces will affect the friction. Where the surfaces are rough, they will say that the friction will be very, very high. Where the surfaces are smooth, we'll say that the friction will be very, very low. In fact, generally in physics, if you are solving a question and you are told that the body is moving on a smooth surface, you are expected to assume that the friction is zero. Friction on a smooth surface theoretically is taken to be zero. So anytime you are solving a question on friction and you are told that the surface is smooth, just take the friction to be zero. So the friction on the surface depends on the property of the surface. It depends on properties such as dryness, roughness, smoothness, wetness. If two surfaces are wet, then we expect the friction to be low. If two surfaces are dry, we expect the friction to be higher. If they are rough, the friction will be higher. If they are smooth, the friction will be very, very close to zero or even zero. So friction depends on the nature of the surfaces in contact. Friction does not depend on area of surfaces in contact. That's the third part. Friction does not depend on the area of surfaces in contact. That simply means that anytime an object is placed on a surface, no matter the orientation or the contact, the surface area, the area of contact between that material and the surface, the friction remains the same. If the material is contacting the ground or the surface with the larger part of its area, then the friction it will have will be the same thing as if it is contacting the surface with the smaller part of its area. For example, if we have a surface, if we have an object whose dimension can be represented this way, if that object is placed on the surface, such that it is contacting the surface with the larger part of its area, the friction it will have, this sense, will be the same friction it will have if we change the orientation of that material, if we allow the material to stand on the lower part of its area. The friction does not depend on the area of surfaces in contact. The only thing it depends on is the nature of surfaces in contact. Are the surfaces smooth? Are they rough? Are they wet? Are they dry? Those are the things that determines whether the friction will be high or low between two surfaces. Friction increases to the same extent. That's the fourth point, the fourth property of friction. Friction increases to the same extent as the force that is causing the motion. Friction increases to the same extent as the force that is causing the motion. What I'm saying in essence is this. If an object is placed on the surface where the maximum friction is 4, let's say the maximum friction is 4 Newton. The meaning is if I decide to push this object with 1 Newton, this object will not move. But if you look at the combination, you will expect that from what we have said earlier, the resultant force will be in the direction of the friction. Friction is pulling with 4 while you are pulling with 1. So we expect this object to move in the direction of friction. Friction, if an object is moving in the direction of friction, that means friction is creating motion. Friction will never create motion. Friction will never assume a value that will make it create motion. Friction's major essence is for it to destroy or make sure that motion does not even take place at all. So anytime friction assume a value that will want it to be greater than the force that is trying to cause the motion so that it will now cause motion on the reverse side, friction will not assume that value. What will happen is, yes, friction is 4, but it will not give you the whole of itself at once. It will try to wash out for the force that you are trying to use to create the motion. If the force you are trying to use to create the motion is 1, friction 2 will be 1. If you increase this force to 2, friction increases itself to 2. If you increase this force to 3, friction increases itself to 3. If you increase this force to 4, friction also ultimately becomes 4. Friction increases to the same extent as the force that is producing the motion or the force that is tending to produce the motion. It is when your force has now equaled the maximum friction for that surface that we can now say that the object is about to move, because you have been able to increase your force to the same extent that it is now equal to the maximum friction. If you increase this by the slightest amount, it is going to beat friction and the object will start to move. There's a maximum friction for every surface, but friction will not give you the whole of its maximum at once. It will give it to you bit by bit. It will wash out for the force that you are trying to use to create your motion, and it will give you that size of magnitude of the force, and it will continue to increase it to the same extent to which you are increasing your own force. It is until you get to a point where you have now equaled the maximum friction that you can now beat friction. Friction will never be more than the force that you are using to create motion. And the last of them, the last of the properties of friction, is that the maximum friction is directly proportional to the normal reaction that is pressing the two surfaces together. The maximum friction is directly proportional to the normal reaction that is pressing the two surfaces together, the surface of the object that is trying to move over another surface. The normal reaction that is pressing them together is what we call, is directly proportional to the friction. And from there, we are going to try to see some relations that we have to learn on friction before we start to solve its problems. Starting with an horizontal surface. Starting with an horizontal surface, when an object is placed on an horizontal surface, we need to talk about the forces that are involved in the object. When an object is placed on an horizontal surface, we need to talk about the forces that are involved. Number one, the object will have a weight. The object is going to have a weight. And like we have said in our previous classes, the weight of an object is always acting vertically downward. The weight of an object is always acting vertically downward, irrespective of the position of the object. Anyhow you choose to place the object, the weight of that object will act vertically downward. Now, the weight of an object wants it to go down. But when you place an object on the surface, on the table, on an horizontal surface, any horizontal surface, it is common knowledge that it stays there. The question is, why is it not falling? Due to the action of its weight. Because the table is supporting it in that same reaction, in the opposite direction with a normal reaction. Normal reaction is a force of support. It is a force with which the surface will use to support the object such that it does not fall. So normal reaction is in the direction that is opposite to the weight. It is not always in the direction that is opposite to the weight. It is in that direction for this particular surface. Generally, I always tell students that the direction of the normal reaction is such that it is always at 90 degrees. It is always perpendicular to the surface. So where the surface is horizontal, the normal reaction will be vertical. Where the surface is vertical, normal reaction will be horizontal. Where the surface is inclined, normal reaction will also be inclined in a way that it will still maintain 90 degrees with the surface. That is why it is called normal reaction. Normal means 90 degrees. Normal means perpendicular. So when the normal reaction is, the surface prevents this object from falling by exerting a normal reaction on it. And we said normal reaction is perpendicular to the surface and it is always away from the surface. It is never going to be towards the surface. So generally, anytime you place an object on the table, this is what is happening. Anytime you place an object on the table, this is what is happening. There's a weight that the object is exerting, there's a weight that comes from the object downward on the table, and there's a normal reaction that the table is also exerting on the object, preventing it from the fall that the weight is trying to give to it. Now, it is this normal reaction that we said that the friction is directly proportional to. The higher the normal reaction, the higher the friction. The less the normal reaction, the less the friction. So if we have this type of situation, we will say that the maximum friction, therefore, is equal to Kr. We will introduce a K, which is the constant of proportionality for this equation. K must now be the friction divided by the normal reaction. Must be the friction divided by the normal reaction. And if that is the case, if K is equal to the friction divided by the normal reaction, it means that K being a constant, there's a better representation for that K, and we use the Greek letter mu to represent it. Mu is equal to friction all over R. This friction will have the same name and description as this friction, this coefficient, this constant we have the same name and description as the friction. Remember, we talked about two types of friction. If the friction is static friction, then this will be called the coefficient of static friction. If the friction is kinetic friction or sliding friction, then this mu will be called the coefficient of sliding or kinetic friction. The name that is given to this friction will ultimately affect the coefficient, the name of the coefficient, or the form of this friction will also describe the form of the coefficient of friction that we're talking about. Now, I am not going to show the friction for two reasons. The friction that I'm going to calculate from this formula is called the maximum friction on that surface, from that surface to the object. So I am not going to show it. To show it, if the object is just left on the table, if I ask you what is the friction as it is zero, because you have not established any motion. It is until you decide to establish a motion by moving the object, by trying to move the object, that friction will establish itself in the opposite direction. If you try to now move it by 1, if you try to move it in this direction with your own force, let me call your force P, the friction will now establish itself in the opposite direction. How will you know that the friction is here? I already said it. There are two things you must consider. Number one, what is the direction of motion? Number two, friction is always along the surface. The friction is always along the surface. It means that if the surface is horizontal, friction will be horizontal. And if the motion you are trying to cause is in this direction, then friction must also be in the opposite direction. Friction wants to prevent what this man is trying to do. So this becomes the friction. Now, we said friction is, it won't give you the whole of itself at once. If, for example, like I said earlier, if I've calculated friction from all of this, and friction is 5 Newton, it is until I decide to push with a force of 5 Newton that the friction will be 5. If I push with a force of 1, the friction will not give me the whole of itself. It will give me just 1. That is one of the that is spelled out in one of the properties of friction. I said friction increases to the same extent as the force that is producing the motion. If the force is 2, friction increases itself to 2. If it is 3, friction increases itself to 3. If it becomes 4, friction increases itself to 4. If it becomes 5, friction increases itself to 5. And remember, 5 is what I said we have calculated from this formula. It means that at that point, the object will be about to move because you have your force is now equal to the maximum friction. You have been able to increase your force to the point that friction can no longer increase itself. So any slight increase or any slight agitation on the object will lead to a movement in the direction of your motion. So that is basically what we have. So there are instances too where whenever we are told that the object is now about to move, anytime we are told that the object is about to move, it simply means that the force you are trying to use to push the object is now equal to the frictional force. The force you are trying to use to move the object is now equal to the frictional force. There are two instances that they can give you that will suggest that the force you are using to push with is equal to the frictional force. Let us consider the relative size of this force, the one you are trying to use to cause the motion, and the frictional force. If P, the force you are using to cause the motion, case 1, is less than the friction, the object does not move. It's less than the maximum friction. The object does not move. The object will not move. It is until you beat friction or you overcome friction that the object will begin to move. So in case 1, when the force you are using to push the object is less than the friction, the object will not move. Number 2, in case 2, if that force is equal to the friction, if the force is equal to the friction, then there are two things that can happen. Number 1, I can say that the object will be about to move, because at that point you have been able to increase the force to the point where it is now equal to the maximum friction. Meanwhile, it is maximum friction that we can calculate from all of this expression. If the force you are using is, if the object is about to move, it means the force that you are using to create motion is equal to the frictional force. Also, when the force you are using to create motion is equal to the frictional force, we can say that the object will move with constant velocity. For an object to move with constant velocity, you don't really need a net force between the force that you are using to move the object and the frictional force. When an object is moving with constant velocity, It is also achieved when P is equal to F friction. When the force is equal to the friction, therefore, there are two things that can happen. Number one is either the object is about to move or it has started moving at constant velocity. Case 3, if the force you are using to create motion is now greater than the frictional force. If the force is now greater than the frictional force, it means there's a net force in the direction of motion. It means a very good example, if I'm pushing with 6 when the frictional force is 5, it means there's now a net force in the direction of 6. It means clearly that the object will now move with an acceleration. The object will now move with an acceleration because before an object can have an acceleration, a net force is required. That is when I will now use my equation F is equal to ma. The force that is causing the acceleration now is not P, it is not F, it is the difference between P and F. The difference between P and F must now become P minus the friction, and that will be equal to ma. I can use that now, if I know the mass of the object in addition, to determine the acceleration with which the object is going to move away from that point. So therefore, if I want to apply this to this particular illustration, I will say that the F that will be responsible to produce the acceleration is 6 minus 5. 6 minus 5 is 1. It means this object is going to start to move with a net force of 1, and that will impact on it an acceleration if I know the mass. So there are 3 situations that we can have. A situation where the force you are using to produce motion is less than the friction. If that is the case, the object will not move at all because you have not been able to overcome friction. If the force you are using to create motion is equal to the maximum friction, then there are 2 things that can happen. Number one is that the object begins to move. It's that you are told that the object is about to move, or the object has even started moving but with constant velocity. Because when an object is moving with constant velocity, acceleration is 0 and no net force is required. Now, in case 3, when the force you are using to produce motion is greater than the friction, when the force you are using to produce motion is greater than the friction, then there will be an acceleration. The object will not just move. There will be an acceleration that will also be impacted on it. That acceleration can be obtained from the formula F is equal to ma, where F is the resultant of P and the friction. Is the difference between P, the force you are using to produce motion, and the friction. Basically, that is all about what we have to treat on horizontal surface. We'll now move on to vertical surfaces. We are still going to come back to solve some example on this aspect. Now we want to see friction on a vertical surface. Friction on a vertical surface. Friction on a vertical surface. If we have a vertical surface like a wall and an object is placed on the wall, of course it will be very difficult to place an object on the wall. Before an object can stay on the wall, there has to be a force that is holding it to the wall. There has to be a force that is holding it to the wall. Now, let me try to show all the other forces that might be involved. I told you objects have weight. Even if you are not so sure of any force that should be in this type of a system, you know that the object will have a weight. And the weight of an object, irrespective of the position of the object, is always acting vertically downward. The weight of an object, irrespective of the position of that object, is always acting vertically downward. It is necessary for us to know that the direction of the weight, whether the object is placed on an horizontal surface, a vertical surface, or an inclined surface, is always acting vertically downward. If that is the case, I need you to also understand that before an object can stay on the wall, there must be a force that is holding it to the wall. Let us call that force P. Let us call that force P, because a force has to hold it to the wall. It can either now be a force that is coming from a person or a force that is coming from an agent that is holding the object to the wall. It could be a glue, it could be gum, it could be so many, it could be a nail that has been used to nail the object to the wall. Now, I told you, whenever you have a surface, anytime you have a surface, there is a force that is acting perpendicularly to the surface. There's a force that is acting perpendicularly outward from the surface. The name of that force is the normal reaction. I gave you normal reaction when we're talking about horizontal surfaces. Now I'm giving you normal reaction when we are talking about vertical surfaces. So normal reaction must have two properties. It must be perpendicular to the surface and it must be outward from that surface. That's normal reaction. Now, the last, of course, if you are holding the object to the wall and the wall is exerting a normal reaction in the opposite direction, the weight is acting vertically downward. The only surface, the only force that is left for us to show is the friction. Now, where do you think the friction will be? Friction always acts along the surface. Friction always acts along the surface. If friction is going to act, it will act along the surface. Because the surface is a vertical surface, friction will also be in the vertical direction. Now, if this object is going to move at all along the surface, based on what I have shown, it will move downward. It cannot move into the wall because there's a force from the wall on it. It cannot move out because there's a force P that is holding it to the wall. The only force that is yet to be balanced by any other force is the weight. That is why when you put an object to the wall, if it wants to fall, it will just fall around the side of the wall. So, if an object is going to fall, it means the weight, in this case, is the force that is responsible for the motion of the object. It means the weight is the force that is responsible for the motion of the object. If the weight is responsible for the motion of the object, is the force that wants to create the motion, the friction will establish itself along that surface. Friction is always acting along the surface, but this time it will establish itself upward. Friction will establish itself upward. It will try to stop the motion that will be produced by this weight. It will try to stop the motion that will be produced by this weight. But whether on an horizontal surface or a vertical surface, something still holds true. The friction is always directly proportional to normal reaction. And I said earlier that this means that friction is equal to mu r. And I said that your mu must become your friction divided by r. If that is the case, the mu is the coefficient of friction, this is the friction, and this is the normal reaction. So this friction and normal reaction are still always related with this equation. Mu is always equal to F all over R. Now, for both cases, for the three cases that we have discussed under horizontal surfaces, let us try to look at those that can also apply for vertical surfaces. Number one, can we have a situation where the force that is trying to create the motion is equal to the is less than the friction? If the weight is less than the friction, because the weight is the force that wants to produce the motion. Now, if this object is going to move, it won't move out of the wall. It won't move into the wall. It can only drop down. So weight is therefore the force that wants this object to move. If that weight that wants to cause motion is less than the friction, this object stays on the wall. That is why it is possible for you to hold object against the wall. When you hold object against the wall, it simply means that this is in a situation where the weight of the object is less than the friction. In a second situation, we can have the weight being equal to the friction. If the weight is equal to the friction, it means this object will be about to drop down, or it will drop down at constant velocity, or it will drop down at constant velocity. That is also possible. The third situation now is obtained when the weight is greater than the friction. If the weight is greater than the friction, it simply means that this object will drop down, and it will drop down this time with an acceleration. When the force that is causing motion is greater than the friction, then there will be a net force that will impact an acceleration on the body. That acceleration, as I said earlier for horizontal surface, I'm going to repeat for this one too. It can be obtained from the equation F is equal to ma. What is the F? The F is the extra force or the resultant force between the greater W and the smaller f. We can easily get that by doing W minus F, the friction, to be equal to what? Ma. So if I know the weight and I know the friction, I can subtract them to know the force, the resultant force, that will now give this object an acceleration once I know the mass of the object. So these are the three situations that are possible for vertical surfaces. We'll now move on to inclined surfaces. If an object is placed at an inclined surface, it is a bit more interesting for us to deal with. Number one, all inclined surfaces must have an angle of inclination theta. All inclined surfaces must have an angle of inclination theta. Now, if I have to show the forces that apply here, number one, I will show the weight. And the direction of the weight is not affected by the surface. I used to tell you, the weight is always acting vertically downward, irrespective of the position of the object. Whether it is placed on an horizontal surface, it is placed on a vertical surface, it is placed on an inclined surface, the weight is always acting vertically downward. If the weight is acting vertically downward, I will show it as W. That is the weight. Now, there will be a normal reaction. Anytime you have a surface, if the surface is horizontal, the normal reaction is perpendicular to the surface and is outward from the surface. If it is vertical, it is perpendicular to the surface and is outward. So if it is inclined, I expect you to know that it will also be perpendicular to the surface. So anything that is going to be perpendicular to an inclined surface must also be inclined. So I am going to draw my normal reaction this way. And I will show that it is making an angle of 90 degrees with the surface. It is making an angle of 90 degrees with the surface. It is making an angle of 90 degrees with the surface. Now, if I extend that direction, we are going to hold on to that I have. Let us now check the horizontal direction too. If this object is going to move, it will either move downward along the plane, or I can push it upward along the plane. Now, one problem with inclined surfaces is that they do not really always follow our y vertical and x horizontal axis. They seem to have their own horizontal and vertical axis that is a little bit modified from the one that we are naturally used to. This is the y and x axis that we are used to, but what we have here looks like a modified y and x. But even with that, we'll still use it because I told you when we're doing vectors and scalar that we can actually resolve in any given direction. We can resolve not just on our x and y, though those ones are the most common axes that we use for resolution. But we can resolve using any other axis that is given to us. Now, when we check the friction, the reason why we need the direction that is along the surface is that must be where the friction will act. Friction is always acting along the surface. If the surface is horizontal, friction is horizontal along the surface. If the surface is vertical, friction is vertical along the surface. Therefore, if the surface is inclined, friction is also expected to be inclined along that surface. So if we are going to look for friction here, we have to look for it on this line that I've drawn along the surface. Don't forget that the normal reaction is already on this line. And I hope you can see that the line that is along the surface and the line that is perpendicular to the surface that gave us the normal reaction are both perpendicular to each other, because the axis of the normal reaction, I said before, must be perpendicular to the surface. It must be at 90 degrees to the surface. If it must be at 90 degrees to the surface, it must be at 90 degrees to the line that is also acting along the surface. Now, with that, we can find, before we move on, anytime you create an inclined surface and you place an object on that incline, if you gradually move the object up, if you gradually move that surface up, you will naturally discover that this object will slide down the inclined plane even without pushing it. If you are just moving this plane up, your own is to move this plane up, you will get to a point where this object must slide down this plane. The question is, with all of these that I've shown, what force is making it to slide down? I hope you know that it cannot be friction. Friction can never be responsible for motion. Friction can never be in the direction in which motion will take place. It is not possible. So if the object is sliding down, there's a force that is pushing it in that direction. And that force is definitely not the friction. In fact, the frictional force will instead establish itself in the opposite direction. It will not establish itself downward along the plane. Never possible. Now, there's a force that is definitely responsible. And I'm going to get to the end of that force now. I want you to look at the weight. The weight here is between our two preferred axes. The weight this time, yes, is vertical. But because our preferred axes are not exactly vertical and horizontal, I will call them the modified Y and the modified X axis, because both of them are a little bit shifted away from the axis because of the plane that we are using. Now, I must let you know that the angle between this inclination, must be the angle between our weight, the direction of our weight, and the direction of our modified Y. That is easy for us to know. When the plane is horizontal, this is our Y. If I move this plane up a little by, let's say, 5 degrees, then we expect this axis, if it is still going to make 90 degrees with our plane, if the plane moves up by 5 degrees, then the axis must also move in this direction by 5 degrees to ensure that it continues to make 90 degrees with that surface. That is very, very necessary. If the plane moves off by 10, anything that will make 90 degrees with it must also tilt by 10 degrees. So this time, our plane has moved up by theta. It means that the modified Y must move away from where our weight is and must establish itself in another direction that is at theta away from that weight. So this angle must also be equal to this angle. Knowing fully well that we now have this angle, I can resolve this weight between these two axes. I can resolve this weight between these two axes clearly now. If you want to resolve what I told you, go and check the class that we had on scalars and vector. We treated resolution. I said you are going to draw the two components beside it. The two directions beside it. We draw the two components in the two directions beside it. The direction that is beside the angle, I said, is cos. So this automatically becomes W cos theta. The direction that is at 90 degrees to that, the other direction that is at 90, if these two directions are perpendicular and one is cos theta, the other one will be obtained from W sin theta. That is how to get two perpendicular components of a vector. Once you know the component that is beside the angle, the other component that is perpendicular to it must be at sin theta. So now, the question as to how or what force is responsible for a falling object. I was saying that when you raise the angle of inclination by moving this plane up, there will be a point that you will get to that this object will naturally slide down. And I ask, what force is responsible for it sliding down? We can instantly see that that force is W sin theta, the component of the weight along the plane. There are questions that will just ask you to find the component of the weight along the plane. The component of the weight itself is W. But now, for the purpose of the plane that we are working with, we have been able to break that W. We have been able to resolve it into two different components. One component is W cos theta, and one component is W sin theta. W sin theta, luckily, is a component along the weight of the object, along the plane of movement, while W cos theta is a component that is perpendicular to the plane of movement. So those are the two components that we have. If that is the case, we can now continue. Now, so if we are told that with the whole of these arrangements, will the object move or not? I can even claim W since I've resolved it. If you have resolved a vector, you don't really need that vector anymore. If you have resolved the vector, you don't need it anymore. What direction do you think this object will move to? It cannot move up along R because W cos theta is pushing it down in that same direction, in the opposite direction. It cannot also move down into the plane because R is preventing it. The only direction through which it can move, the only direction that we have a force that is not balanced is W sin theta. And that is why generally when you raise the angle of inclination by pushing an inclined plane up, it will naturally roll down because there's a W sin theta that will want to roll it down. In that case, friction will immediately establish itself. The moment you have a force that is responsible for motion, the moment you have a force that is not opposed by anything that wants to create motion in its direction, friction will tend to prevent that motion in its direction by establishing itself in the opposite direction. So friction, number one, must act along the plane. We have always said that, and it must be against the direction of motion of the object. This is the friction. That's the friction. So for this problem, that is what we have. That friction is what we have. So what is the force that is trying to create the motion on this object is W sin theta. What is the force that is preventing the motion? It is friction in the opposite direction of W sin theta. There is R which is acting perpendicularly to the surface, and there's a W cos theta that is also preventing R from having any motion effect on the object. Remember that even here, once again, and in all cases, friction is always directly proportional to the normal reaction. That means if I know normal reaction, I can use it to find the friction. So friction must be equal to mu R. If friction is equal to mu R, then I can say that mu is equal to friction over R. And that is what we have here. Now I'm going to bring up the three cases that I explained for both horizontal and vertical. It also applies here too. In the first case, if the force that is trying to cause the motion is less than the friction, the force that is trying to cause the motion is W sin theta. If it is less than the friction, the object will not move at all. If W sin theta is less than the friction, the object will not move at all. It means the friction will have its day on the object. Number two, case 2. If the force that is trying to cause the motion, W sin theta, is equal to the friction, it simply means that the object will move or will be about to move or will move with constant velocity. It will move with constant velocity down the plane, or it will just be about to move. In both cases, the W sin theta is said to be equal to the maximum friction. Now, the third case, if W sin theta is greater than the friction, if W sin theta is greater than the friction, it means that W sin theta being greater than the friction simply means that the object will now move with an acceleration because there's a resultant force that is available for acceleration. The object will now move with an acceleration that will be impacted on it. So we can now use the formula F is equal to ma. What is F? F is the resultant bit of W sin theta and R. If F is the resultant of W sin theta and R, F becomes W sin theta minus the friction, W sin theta and friction, sorry. It becomes W sin theta minus friction is equal to ma. It becomes W sin theta minus friction, and that is equal to ma. In that case, then we can get the force and we can get the acceleration that is impacted on the object once we know the mass of the object. And that is what we have for this particular problem. I must also go back to the case 2. There's a derivation that can be made when W sin theta is equal to the friction. If W sin theta is equal to the friction, meanwhile, I must also tell you that At all times, the normal reaction and W cos theta must be equal if there is no other force in this system. The W sin theta must be counterbalanced by the normal reaction must be counterbalanced by the W cos theta. So if normal reaction is equal to W cos theta, and we get to a situation where the friction becomes equal to W sin theta, we can now bring up this expression to find the coefficient of friction, which is the friction divided by the normal reaction. The friction in that case must be W sin theta divided by the normal reaction. The normal reaction in this case will be W cos theta. If we divide them, we will have mu is equal to sin theta divided by cos theta will be equal to tan theta. So when the object is about to move, or when the object is moving with constant velocity, such that we can say that the normal reaction is equal to W cos theta and the friction is equal to W sin theta, then the mu, the coefficient of friction at that time, can just be equal to tan theta, provided there's no other force apart from the one that I've shown on the board. So anytime you are told that an object is placed on an inclined plane and the object is about to slide down, it simply means that mu is equal to tan theta. If it's about to slide down, that means this is the case, and there's no other force. If there's another force, then we seriously have to consider the placement of that other force. And I'm so sure that at that time, mu cannot be equal to tan theta. So I hope we have been able to treat quantitatively the concept of surfaces, inclined, horizontal, and vertical surfaces as regards friction. We'll now start to take questions based on each of these three surfaces to see what we can have. A horizontal force of 10 Newton is required to just slide a block of mass 4 kg on a horizontal platform. The coefficient of limiting friction between the block and the platform is dash. Number one, know the surface on which you are working. It is an horizontal surface, an horizontal platform. On it, we have an object. We are told that the object has a mass of 4 kg. If the mass of the object is 4 kg, that means its weight is expected to be 40. How did I get the weight? Know that the weight is equal to the mass times acceleration due to gravity. The mass is 4. It means the acceleration due to gravity will be 10. So that will be 40 Newton. So the weight is 40 Newton. Now we are told that the horizontal force of 10 is required to just slide the block. If you are sliding the block, you have to move it, and you are moving it with a horizontal force of 10 Newton. If you are moving it with a horizontal force of 10 Newton, that is the force that wants to produce the motion, because we believe it will have friction. If it's going to have friction, that is why we are also told that this 10 is just sufficient to move it. When they use those words, it's just sufficient, or is about to move, or is moving with constant velocity, there's an equality between the friction and that force. Mind you, there's still one more force that we need to show, and that's the normal reaction. Must be equal to 40 Newton. How did I get that 40 Newton? It is directly opposite the weight, and since there is no movement in that direction, we are not expecting any movement in that direction, we expect the normal reaction to be equal to 40. So if the normal reaction is equal to the weight, which is equal to 40 Newton, and the friction is equal to 10, not that the friction is the force that wants to cause the motion, but the force that wants to cause the motion is 10. And we are told that that force is required to just slide. When they put those words, just slide, about to move with constant velocity, it means the force that is trying to cause the motion is equal to the frictional force. And the frictional force will act in that direction. So with these two, I can now find the coefficient of friction. Know fully well that the friction is equal to mu r. That means mu must be equal to friction all over r. What is the friction? 10. What is R? 40. What is 10 divided by 40 is 0.25. That is the answer to that question. Coefficient of friction does not have units because we are dividing two quantities that have the same units. One is in Newton, the other is also in Newton. Even if they have not been given in the same units, you must convert them to the same units before you can get the coefficient of friction for that surface. Now we can move on. We are also told here that a body of mass 8 kilogram rests on a horizontal surface. There's a horizontal surface. We now have a body whose mass is 8 kilogram resting on it. If the mass is 8 kilogram, I expect you to know that the weight must be 80. That is the weight, it must be 80 Newton. How did I get 80 Newton? The weight is always equal to the mass times acceleration due to gravity. If the weight is 80 Newton, then we'll move on. We are told that a body of mass 8 kilogram rests on a horizontal surface. If the coefficient of friction between the body and the horizontal surface is 0.65, calculate the minimum horizontal force enough to just move the body. We are given the mu that we found in this case, the mu that we found to be 0.65. We now want to find the horizontal force that will just be enough to move the surface. Now, let me indicate that horizontal force as P. If there's an horizontal force that is trying to move it, there must be a friction that is trying to prevent what that will do. There will be a normal reaction that will eliminate the effect of the weight. So we expect that the normal reaction in this question will be equal to 80. It will be equal to the weight. This is directly opposite the weight. So we can find the friction clearly as mu R. When you know mu, you can get friction. Mu is 0.65 and the normal reaction has been found to be 80. So I can do the friction is equal to 0.65 times the normal reaction, which is 80. 0.65 times 80 in this case is 52 Newton. Now, if 0.65 times 80 is 52 Newton, it means the frictional force is 52 Newton. And if that is the case, the force that is trying to produce the motion must also be equal to 52. Because a particular expression was used, they said we should find the horizontal force that will just be enough to move the body. If it is just going to be enough to move the body, it is equal to the friction. When they use those type of phrases, just about to move, just enough to move, moving with constant velocity, always remember that what they are indirectly implying is that the force that is trying to cause the motion is equal to the friction. So once you know the friction, it is the force that is trying to cause the motion. Once you know the force that is trying to cause the motion, it is the frictional force. Now let us take questions on vertical surfaces. We wish to take more questions on vertical surfaces, and we have one here. We are told that a block of mass 150 grams is pushed against a vertical wall with a horizontal force of F Newton. If the coefficient of friction between the book and the wall is 0.15, the minimum value of F required to hold the block in place is dash. Here we have a vertical wall. There is now an object. We are told in the question that the object has a mass of 150 grams. If it has a mass of 150 grams, we must find its weight. The weight is equal to mg, but we cannot use mg until you express the mass in kilogram. So I have to change the mass to kilogram, so such that the mass that is 150 grams, I will divide it by 1000. If I do that, the mass becomes 0.15 kilogram. If the mass is 0.15 kilogram, the weight must be mass times acceleration due to gravity. That will be 0.15 multiplied by 10. 0.15 multiplied by 10 is 1.5 Newton. If it is 1.5 Newton, I can show it now as a downward force. That is 1.5 Newton. If that is the case, I can now start to show other things as the question has given them to me. I was told that the book, which is of mass 150 grams, is pulled against a vertical wall with a horizontal force of F Newton. This book is pulled against the wall with a horizontal force of F Newton. That force was not given. It's pulled with a horizontal force of F Newton. The question now is, if the coefficient of friction between the book and the wall is 0.15, if the coefficient of friction between the book and the wall, coefficient of friction is represented by mu, we are told by the question that it is 0.15. Is 0.15. The question now is, what is the minimum value of F required to hold the block in place? What must be the smallest value that F will be before this object can be in position as it is? In doing so, I will show the other forces based on the treatment of vertical walls that we have talked about, friction on the vertical plane that we have talked about. We will show the normal reaction R. The normal reaction is always out of the surface and is perpendicular to the surface. If the surface is vertical, the normal reaction will be horizontal. If the surface is horizontal, the normal reaction will be vertical. There's one more. If the object is to be left like this, it will fall down by the action of its weight. So the force that will prevent that falling, which is also a form of motion, must be the frictional force, and it must be against the direction of the weight, since the weight is now the force that is trying to create the motion. So we can easily just say that if this object is to remain in position, then the friction must be equal to 1.5, upward force is equal to downward force, and R must be equal to F. The forces to the left must be equal to the force to the left must be equal to the force to the right. So if friction is known to be 1.5 and I already know the coefficient of friction to be 0.15, I can use my expression for friction, which is friction is equal to mu R, to find mu. My mu outrightly becomes friction all over R, and my R becomes friction divided by mu. My friction is 1.5 Newton, while my mu is 0.15. If I divide 1.5 by 0.15, I will have a normal reaction that is equal to 10, that will be equal to 10 Newton. So the normal reaction being 10 Newton, and we have already said that the normal reaction must be equal to F. It clearly therefore means that the F that will hold this object or this book in position must also be equal to 10 Newton. So that is an example of questions that we can have on friction on a vertical plane. We will now take some questions also on friction on an inclined plane. A body is in limiting friction. A body is in limiting equilibrium on a plane inclined at an angle of alpha. A body is in limiting equilibrium on a plane inclined at alpha to the horizontal. If cos alpha is equal to 0.8, calculate the coefficient of friction. We are told that the body is in limiting equilibrium. A body is in limiting equilibrium. Limiting equilibrium is one in which all the forces, the basic forces that are there, are equal to each other as we treated it under inclined plane. We said we are told that it is inclined at alpha. We are also given that cos alpha is equal to 0.8. We are now asked to find the limiting friction. Don't forget that while we're talking about inclined plane, we said that the forces that we're able to get are, number one, the normal reaction, which is in this direction. Number two is W cos theta, which is in this direction, W cos theta. Number three is W sin theta, which is downward along the plane, W sin theta. Number four is the friction, which will prevent the effect of W sin theta that wants to cause the motion. And we said if it is in equilibrium, it means forces in all directions have completely counterbalanced each other. So we can say that the friction is equal to W sine theta. And we can also say that R is equal to W cos theta. If that is the case, we can use our equation friction is equal to mu R. If that is the case, mu becomes friction all over R. If that is the case, friction is W sine theta and R is W cos theta. If we know that W cancel out W, mu is equal to sine theta divided by cos theta in mathematics is tan theta. This time the theta is alpha. So what they want me to find, the coefficient of friction, I will get it by doing the tan of the angle that is given to me. The angle has not been directly given. Instead of giving me the angle, they give me the cos of that angle. From the cos of that angle, I can find that angle. If I want to find it, alpha must be equal to arc cos of 0.8. And the arc cos of 0.8 is what I would find as 36.87. 36.87 degrees. So my mu, which is the coefficient of friction, will be tan of 36.87, and the tan of 36.87 should be, the tan of 36.87 is 0.75, and that is the coefficient of friction for that surface. We'll take more examples on inclined plane because those are really the ones that always pretend to give students issues. Now we have other questions that we are going to look at. A body of mass 4.5 kilogram rests on a smooth plane inclined at an angle of 47 degrees to the horizontal. Calculate the magnitude of the force P parallel to the plane just enough to prevent the body from sliding down the plane. Now we have an inclined plane, clearly from the question. The plane is inclined at 47. Generally, when you solve questions like this, the question can initially look as if it is difficult. But what I always advise students is you must start solving a question from the place of knowledge. You must start from the point that you know, and you gradually proceed. As long as you are in class, when the concept is treated, you must be able to maneuver your way through to the solution. But generally, don't look at a question with the eye that you cannot solve it, with the mindset that it is looking too difficult. You can always start from the point where you know. Number one, if I have an inclined plane, I will draw the inclined plane. I will show the angle of inclination. Those are necessary details that I must show. I must also put the object on the inclined plane, and I must show my modified x and y axis on the plane. My modified x and y axis are what I will show on the plane. If I do that, we have been told that the object has a mass of 4.5 kilogram. It has a mass of 4.5 kilogram. Because its mass is 4.5 kilogram, the weight must be 4.5 kilogram times 10, and that will be 45 Newton. So, and I know that what we use here is not exactly the weight. What we use here are the components of the weight. These are details that can never change on an inclined plane. While there are some other details that can change, W sin theta and W cos theta's direction are fixed. Anytime you are solving a problem on an inclined plane, they can never change. So this will be my W cos theta. My W cos theta will be 45, no, my W sin theta, 45 sine 47 degrees. While this will be my W cos theta, that will be 45 cos 47. Those two can never change. Those two can never change. Now we move on. We are told that we should calculate the magnitude of the force P that is parallel to the plane, just enough to prevent the body from sliding down the plane. Why is that necessary? We expect the friction to be the force that will prevent the object from falling down. Let us indicate the friction. Let us indicate the normal reaction. Probably by the time we solve all of this that we know, we should understand what we are talking about. We are given the G to be 9.8 meters per second. Now, we want to include, we are told that this object rests on a smooth plane. We are told that this object rests on a smooth plane. One very good detail that you must know for objects that rest on smooth plane, I said it earlier, is that there will be no friction. When the surface is smooth, there will be no friction. So that is the only exception to what we already have that I'm going to introduce here. When the surface is smooth, there is no friction. That is why instead of friction, they are now asking for a force that is parallel to the plane, which is enough to prevent the body from sliding down. Normally, this object will slide down. It will not go up because there's a 45 cos 47 that is downward. It will not come down because there's a R that is upward. Now, but it will move in this direction. Normally, if the surface is smooth and there's no friction, this force has not been balanced. And because this force has not been balanced, this object will go in the direction of this force. That is why they are now asking for a force P that will be put along the surface that will prevent it from sliding down. The force that will prevent it from sliding down must go against the direction of sliding down. So that also is a force that looks like friction. We are not just going to call it friction because this is definitely not friction. It is probably a force that comes from a person that is trying to hold the object up such that it does not fall. There's no friction on this surface because the surface is smooth. But there's now someone that is trying to prevent it from falling, and that is the force that they want us to find. How do I know that this is how the force must look? Listen to the question. They said that I must find the force P that is parallel to the plane, and it must be enough to prevent the body from sliding down. It must be parallel to the plane. It must be along the plane, and it must not allow this object to fall down. If this object is going to fall down, whatever will prevent it from falling down must be directed upward along the plane. You can show it like this, but you can also show it like this. Just show something that is upward, and that is correct. So if I want to find P, if P is going to be able to prevent this object from sliding down, it must be up to what is required to balance the force that wants it to come down. So P must just be equal to 45 sine 47 degrees. That is all. Sometimes some questions will look so big, mighty, and difficult to solve, whereas what is required to solve them is just something very, very simple and easy. 45 sine 47 is equal to 32.91. So the force must be equal to 32.91 Newton. And that is my answer for this question. We are now going to proceed to more questions on inclined plane. We are told here that a body of mass 5 kilogram rests on a horizontal plane. A force P inclined at an angle of 40 degrees to the horizontal is sufficient to move the object. If the coefficient of friction is 0.3, calculate the magnitude of the force P. A body of mass 5 kg rests on a horizontal plane. This is a question on an horizontal plane, but we are going to see why I've decided to solve it. We have an object on an horizontal plane. His mass is 5, so we expect his weight to be 50. Remember how we show weight on an horizontal plane. The weight is 50 Newton. We are also told that it rests on an inclined plane. There's now a force P inclined at an angle of 40 degrees to the horizontal, which is sufficient to just move the body. So it is the force that wants to move the body that is now inclined, not the body itself, not the surface. The surface is horizontal, but the force that wants to move this surface is inclined. There's a force. That force is called a force P. It is inclined at 40 degrees to the horizontal. This is the horizontal. It is inclined at 40 degrees to the horizontal. That force is inclined at 40 degrees to the horizontal. And it is just enough to move the body. It is just enough to move the body. If the coefficient of friction is 0.3, the coefficient of friction mu is equal to 0.3 on this surface. We are expected to calculate what's the magnitude of P. Anytime you have an inclined force on an horizontal or vertical surface, you must resolve it. You must resolve it. That is when you will understand what role is going to play in the process leading to the solution to the question you are solving. Now, if I want to resolve it, I already told you how to resolve. You draw the two axes beside it, the horizontal axis and the vertical axis. The horizontal axis, the horizontal component will be P cos 40, while the vertical component will be P sin 40. That is it. Once resolved, I can clean the original vector. It is of no use to me. And by now, you should start to understand the topic one step at a time. So we can now get the friction moving in the opposite direction. It has a friction because it has a coefficient of friction. Why did I know that the friction is in this direction? Definitely this P cos 40 is trying to move that object. There's one more force that I have not shown. That's the normal reaction. So I'm going to show the normal reaction in the direction that it should be. The question now is, why should the normal reaction be this? I thought the P sin 40 should be the normal reaction. No. A force that is not normal reaction cannot be the normal reaction. It can take the position of normal reaction, but normal reaction will still be there. And normal reaction is always going to be there as long as there's a surface. What that force can do is to add to the total forces upward, but there will still be a normal reaction there. There's nothing that will not make a normal reaction to be exerted from the surface. So from this, we are told that the object is just about to move. If it is just about to move, please always understand that there's an equality of forces. There is an equality of forces in all directions. It means that the total forces upward, R plus P sin 40, must be equal to 50. So the only thing the P force has been able to do is to increase the number of items required for our equilibrium equation. So we can also say that the sum of forces in the left direction must also be equal to the sum of forces on the right direction. So that way we can say that friction must be equal to P cos 40. If that is the case, please don't forget also that our friction is equal to mu r. If our friction is equal to mu r, we can outrightly say that friction is equal to mu 0.3 multiplied by r. Friction is 0.3 and it is equal to r. We have been asked in this question to find the value of P. So I can substitute for friction. If I substitute for friction, I will have 0.3 r is equal to P cos 45, sorry. If I put this in an equation form, it becomes 0.3 r minus P cos 40 is equal to 0. I can now solve it simultaneously with the first equation that I have, which is r plus P sin 40 is equal to 50. I can directly make r the subject of the formula here. That will be 50 minus P sin 40. If that is the case, I can now substitute for r in this equation. If I substitute, I will have 0.3 open bracket 50 minus P sin 40 is minus P cos 40 is equal to 0. If that is the case, I can multiply 0.3 times 50 is 15 minus 0.3 times this is 0.3 P sin 40 minus P cos 40 is equal to 0. If that is the case, then I can clearly say that 15 minus, let me multiply the two things that I can solve for there. I can solve for 0.3 sine 40. That should be 0.193p minus cos 40. 0.766p must be equal to 0. So 15, I will add all of this. I will have 0.766 plus 0.193. That should give me 0 minus 0.959p. It is equal to 0. If I collect like times, I will have 0.959p is equal to 15. P therefore must be equal to 15 divided by 0.959, and that should be 15 divided by 0.959. That will be 15.641 Newton, which is the answer to this question. Now, I think we have been able to solve sufficient number of questions across all the three planes that we can have for friction. We have solved questions on horizontal, on vertical, on inclined plane. We have even solved questions that require the use of an inclined vector on an horizontal plane. Friction has advantages, it has disadvantages. The friction majorly has disadvantages. The disadvantages of friction includes the fact that friction is what is responsible for why the efficiencies of machine is not 100%. Friction causes wear and tear in machine, and it produces heat even when they are not needed in the operation of machine, thereby reducing the efficiency of those machines. But all about friction is not just disadvantage. Friction serves a lot of other advantages, majorly among which friction is what makes walking and running possible. Without friction, objects will be sleeping while running or walking. Humans will be sleeping on the road while walking or running. And friction is also very necessary in all other areas of physics. There are different methods that can be used to reduce friction in cases where friction forms disadvantage. We can have lubrication, where we can lubricate the contacting part between two metals with oil or grease to reduce friction within machined element so that we can boost its efficiency and make it work better and generate less heat. One other thing that we can do is we can streamline the moving parts of bodies, so we also reduce friction so that moving objects can move freely through segment of air to reduce the resistance of air that comes from friction. And the last thing, we can use roller bearings at the base of moving objects to further reduce friction. We can use roller bearings to reduce friction, and these are methods that we can use to reduce friction. Until next time, thank you for joining us this class.